Hey everyone, today we're going to dive into something you've probably wondered about yourself. How on earth can a camera read the license plate on a car that's just flying by? We're going to break down the incredible AI that makes it all possible and what it tells us about how we're teaching machines to actually see the world.
Seriously, just think about it for a second. A car is speeding past, maybe it's dark out, maybe it's even raining, and yet some camera can instantly find that tiny little rectangle and read every single character on it. It seems like magic, right? Well, it's actually a brilliant piece of artificial intelligence that really gets to the heart of a huge challenge in tech called computer vision.
So the main problem that computer vision scientists are trying to solve is just the unbelievable amount of visual data out there. I mean, there are millions of cameras recording 24/7. It is physically impossible for humans to watch all of that. So we have to automate it. We have to teach machines to watch for us and, give us a nudge when something important happens. But for any of these automated systems to actually be useful, they have to be reliable. They've got to avoid two really critical errors. The first one is a false positive. That's like a security camera flagging a leaf blowing by as an intruder. It's a little annoying, but not the end of the world. A false negative, though, that's missing the actual intruder. That's a huge problem. So for any AI that sees, getting this balance right is, well, it's everything.
So to solve this problem, computers can use different strategies to find things, kind of like we do. We're going to take a look at two major approaches. One that's pretty simple, and another one that's way more powerful and modern.
Okay, so the first method is called background subtraction. The idea is actually pretty straightforward. Imagine you take a picture of an empty street. The computer saves that picture as the background. Then it just compares every new frame from its video feed to that original picture. Anything that's different, a person walking by, a car driving past, it just instantly pops out. It's simple for sure, but it can be super effective when the background isn't changing much.
Now for the really smart approach, an algorithm with a fantastic name, YOLO, which stands for You Only Look Once. See, unlike older methods that would painstakingly scan an image piece by piece, YOLO looks at the entire image all at once. It's a lot like how you can just glance at a photo and instantly know that's a person, that's a car, that's a building. It processes it all in one single pass. It was a total game changer for speed and efficiency.
And this slide right here, it perfectly sums up the fundamental dilemma that AI engineers face every single day. Just look at the numbers. Background subtraction is incredibly fast, less than a second, but it only catches about 84% of what it's looking for. YOLO, on the other hand, is way more accurate at 90%, but look at that, it's over 5 times slower. This forces a critical choice for any system you build. Do you need an answer right now, or do you need the right answer? So that brings us right back to our license plate. For a job this precise, accuracy is absolutely king. So let's see how that powerful YOLO algorithm, specifically the latest version YOLO 8, is used to build a real-world automatic license plate recognition system, or ANPR. The way engineers solve this is brilliant. They break the big problem down into a simple 3-stage pipeline. Instead of trying to do everything at once, the system first finds the car, then it zooms in to find the plate, and only then does it even try to read the characters. Let's walk through how each step works.
Okay, so for step 1, the system takes a really smart shortcut. It doesn't waste its time and energy scanning the entire scene for a tiny little license plate. No, instead it uses a general-purpose YOLO model, one that's been trained on millions of images of all sorts of things, to quickly find the big objects. It just draws a box around any car it sees, and by doing that, it gets to ignore all the useless background noise. Now, for step 2. The system takes that little cropped image of the car and hands it off to a specialist. This is a second YOLO model, but this one has been trained on thousands and thousands of images of just one thing: license plates. Its entire job is just to find that little rectangle with extreme precision and cut everything else out.
But hold on, we can't read the plate just yet. That cropped image might be a little blurry or too dark, or maybe it's at a weird angle. So in this supercritical third step, the system basically becomes a photo editor. It applies all these filters to sharpen the image, it boosts the contrast, it cleans up any noise, all to make the characters inside that box as crystal clear as possible for the final step. And at last, the cleaned up image gets sent to what's called an optical character recognition engine, or OCR. This is yet another AI model, but its one and only job is to recognize letters and numbers. It turns the pixels into actual text, and just like that, the system has successfully read the license plate. It's a perfect example of the power of breaking a really hard problem down into a series of smaller, much more manageable steps. But as we saw a little earlier, building a system for the real world isn't just about getting the right answer.
It's also about how fast you can get it and how much computing power it's going to take. This is the constant balancing act for AI engineers.
I mean, a system running in some giant data center has basically unlimited power. But what about a system that needs to run directly on the traffic camera itself, or on a police officer's smartphone? These are what we call resource-constrained devices, and they need a whole different approach. To solve this, the creators of YOLO V8 actually offer a whole family of models. As you can see in this table, they go from N for nano all the way up to X for extra large. The smaller models, like the nano one up top, have lower depth and width values, which basically means they're simpler and faster, perfect for a small device. The larger models down at the bottom are more complex and more accurate, but they need a lot more power. This gives developers a whole menu of options to pick the perfect tool for whatever job they're doing.
And what's just incredible is how good even these smaller models are. Research shows that the YOLO V8S model, that's the small one, can achieve a 99.3% mean average precision. Now, that's a fancy technical term, but it basically measures how well the model both finds the object and correctly knows what it is. To get that kind of accuracy while still processing video in real time is a massive achievement for these low-power devices.
Hey, remember that image processing step we talked about? This is exactly why it matters so much. One study found that by using some smart sharpening and other techniques, they could boost the final accuracy of the character reading by over 5%, especially in really tough low-light situations. Sometimes it's these small, clever tweaks that make all the difference.
So we have systems now that are incredibly fast and accurate. What's the next big challenge? Well, the next frontier in computer vision is all about energy. How do we get these systems to do their job while using the absolute minimum amount of power possible?
Here's the problem. A typical video camera is always on. It's capturing 30 full pictures every single second, even if absolutely nothing in the scene is changing. Just imagine a security camera watching an empty hallway all night. All of that recording and processing, it's just wasted energy.
So now, researchers are looking at a whole new type of sensor, one that's actually inspired by the biology of the human eye. It's called a neuromorphic event camera. Unlike a normal camera that captures everything all the time, an event camera is, well, it's event-driven. Its pixels only turn on when they detect a change in light. It only sees motion. This makes it unbelievably efficient. We're talking less than a third of the power of a normal camera.
This leads to a brilliant hybrid approach, which you can see in this diagram of a system called NeuroVig. Now don't worry about all the boxes here, just follow the main idea. Over on the left, you've got two inputs, the low-power event camera and the main video camera. The event camera acts as a trigger. When it senses motion, it wakes up the main camera, which then captures one high-quality picture. The system then processes only that important picture, saving a massive amount of energy.
And the results are just staggering. This intelligent trigger system reduces the total energy used by a factor of 4, and it cuts down the processing delay, the latency, by almost as much. And get this, it does all that with less than a 1% drop in accuracy. It is truly the best of both worlds. You get smart, powerful analysis, but only when you actually need it.
So from simple motion detection all the way to these hyper-efficient, AI-powered systems, we've seen how computers have learned to see. The technology is getting faster, more accurate, and more efficient every single day. And that leaves us with one final and pretty important question. As these powerful digital eyes become more and more a part of our world, what should we be asking them to look for next?